Hey everyone, and welcome to this explainer. Every time you stream a movie, save a document, or back up a photo from your phone, you are actually interacting with incredibly complex physical machines. Today, we're going to ground something pretty elusive, the cloud, into cold, hard reality. When we talk about the cloud, it's really easy to picture our data just sort of floating around in some ethereal, invisible space, right? But the truth is much heavier, way more mechanical, and honestly, infinitely more fascinating. Because get this. A staggering 70% of all the world's information right now lives on physical hard drives. Now, sure, flash memory in our phones and laptops is growing incredibly fast, but when it comes to the massive exabyte scale storage required by modern data centers, hard drives absolutely dominate. They're just vastly cheaper. So today, we're going to zoom all the way in to see exactly how these remarkable machines actually work. Here is our flight plan for today. First, the engine of the cloud. 2. Anatomy of a hard drive. 3. The superparamagnetic limit. 4. Cheating physics with heat. And 5. Engineering at the nanoscale. Okay, let's jump right into section 1, the engine of the cloud. Before we dive all the way down to the atomic level, let's just look at the incredible scale of these drives over time. Because remember, every single digital action you take relies on a physical spinning disk somewhere out there in the world. Our journey starts back in the 1950s with the IBM RAM-EC. This absolute beast of a machine literally took up an entire room. It used spinning disks that were 52 inches across and held a whopping total of 5 megabytes of data. Yeah, 5. Fast forward to the early 2000s, and the industry had shrunk things all the way down to 1-inch micro drives, which actually powered those early consumer devices like the iPod. Remember those? But today, it's all about the cloud. The fastest growing part of the market are these 3.5-inch drives, hermetically sealed, packed with helium, powering massive exabyte-scale data centers. It honestly blew my mind to learn that since the 1950s, the areal density of these drives has grown by a factor of almost a billion. A billion. Moving right along to section 2, anatomy of a hard drive. Let's actually look at the mechanics of how this data is physically read and written. To really grasp the sheer mechanical insanity of a modern hard drive, try this analogy. Imagine if you took the disk and scaled it up to the size of the entire San Francisco Bay Area. At that scale, the little slider reading the data would be the size of a fully loaded 747 airplane. And that airplane would be flying just 4 millimeters above the ground. Oh, and to maintain the same data rate we have today, that 747 would have to be traveling at roughly 10% of the speed of light. The physical tolerances we're talking about here are just a few nanometers. So operating at those extreme tolerances, you've got this actuator arm moving back and forth across tracks on the disk. And those tracks are so unfathomably narrow that engineers currently fit about 300,000 of them into just a single inch of the disk's radius. The data is stored magnetically in these tiny domains as ones and zeros, oriented north or south. Now, for decades, these magnetic bits laid flat, totally parallel to the surface of the disk. But to pack more data in, the industry had to make a massive leap. They decided to stand the magnetic bits upright. By pointing the bits perpendicular to the disk and adding this special soft magnetic layer underneath to act almost like a mirror, engineers could concentrate the magnetic field. This was a total game changer. It allowed us to drastically increase data density without the bits accidentally erasing each other. But that brings us to section 3, the superparamagnetic limit. This is the dramatic conflict of our explainer. We are currently slamming into a fundamental wall of physics. To store more data, obviously, we have to make the magnetic grains smaller. But there's a terrifying nanoscale phenomenon just waiting for us. When these grains get too small, the energy barrier that keeps their magnetic direction stable starts to drop. Eventually, they get so incredibly tiny that just the ambient thermal energy of a normal room temperature environment is enough to overcome that barrier, which means the bits spontaneously flip and erase themselves in a matter of microseconds. This is known as the superparamagnetic limit. The whole thing really boils down to this brutal mathematical tug-of-war. To guarantee your data survives for years and doesn't just vanish, the energy barrier holding it in place has to be much greater than the ambient thermal energy. Since we're shrinking the grains, our only choice to maintain that stability is to use magnetically hard materials. But here's the catch. The magnetic field required to actually write a bit is tied directly to that hardness. If we use materials hard enough to be stable, they require massive magnetic fields. We're talking over 2 Tesla just to write the data. And those are the stakes right there. Conventional write heads max out at generating about 1 to 2 Tesla, so we are currently stuck using grains that are about 8 nanometers across. If we try to go smaller with today's materials, the data literally erases itself. But if we switch to harder materials, our write heads physically cannot generate a strong enough magnetic field to record the data in the first place. At room temperature, the scaling of global data storage just stops right here.
Enter Section 4, Cheating Physics with Heat. So if you can't beat the laws of thermodynamics, you kind of have to bend them. And this is exactly where heat-assisted magnetic recording, or HAM, comes in. It's this brilliant four-step sequence. First, a laser diode mounted right on the slider fires down into a waveguide. Second, it hits a near-field transducer, which creates this crazy sub-wavelength plasmonic hotspot that blasts the tiny magnetic grain up to about 500 degrees Celsius in a single nanosecond. Literally a nanosecond. Third, as the temperature spikes, the material's magnetic hardness plummets, and the standard magnetic head can now easily flip the bit. Finally, as the head flies away at immense speed, the medium cools back down instantly, locking the data permanently in place with its natural, extreme room temperature hardness. It's honestly incredible how seamlessly this solves the puzzle.
But what's really surprising about this whole process is just the sheer inefficiency of it. Because the process of turning laser light into actual heat on the disk is so indirect, less than 1% of the power actually reaches the disk. That means dealing with that other 99%, the heat dissipating straight into a tiny head flying nanometers above the surface, is one of the absolute hardest engineering challenges in the entire industry right now.
Which leads us perfectly into Section 5, Engineering at the Nanoscale. To actually survive this incredibly violent, high-speed heating and cooling cycle without just melting the drive, we need some very exotic materials. First off, HAMR uses iron platinum. It has an energy barrier 10 times higher than current materials, meaning it can hold incredibly tiny bits safely. Second, the antenna acting as the optical heater, it's actually made of gold. It functions basically like a nanoscale lightning rod to concentrate light far below the standard diffraction limit. And finally, the whole environment is sealed in a helium atmosphere. Since helium is 7 times less dense than air, it massively reduces drag, vibration, and temperature turbulence inside the casing. Keep in mind, this whole operation is happening on a slider the size of a speck of dust. It takes a staggering 1,000 distinct processing steps to build just one of these nanoscale read and write heads on a silicon wafer. And the industry makes about 100,000 of these devices on a single 8-inch wafer. It is an absolute masterpiece of mass-produced, high-precision physics. By conquering these limits, heat-assisted magnetic recording is poised to scale our data capacity from around 1 terabit per square inch right now up to roughly 4 terabits. And if engineers can eventually master lithographically patterning the disk into perfect little islands instead of random grains, we could potentially push this to 10 terabits and beyond. For sure, the physical hard drive is going to remain the engine of the cloud for decades to come. Which kind of leaves us with this final provocative thought. As we continue to shrink from chunks of metal down to 8 nanometer grains and eventually to perfectly arranged molecular islands, you really have to wonder, what is the absolute floor? Could we eventually control the magnetic spin of a single atom to hold a 1 or a 0? The physics of data storage are pushing the very boundaries of our universe right now. I hope you found this breakdown as fascinating as I do. Thanks so much for joining me on this explainer, and keep wondering about the incredible physical world powering your digital life. See ya.